in Navrashna University in Data Science and Mathematics Department. And he's registered as a PhD student from in the area of speech recognition. And he has working experience, teaching experience of like more than 7 years in applied mathematics, MS University of Baroda. And he did his MSc in applied mathematics and industrial mathematics. So he's a very much expert in all this soft computing subjects and this applied mathematical subjects. So let us start this session with Shardav Bhatt. So Shardav, can you please start?
Yes, madam. Thank you, madam. Thank you for the introduction. I'm going to share the screen. Okay, is my screen visible to all?
Yeah, it's visible.
Yes, ma'am. Yes, sir.
Okay.
Visible.
Thank you very much.
But sir, sorry to interrupt you, but your sound is very low. Can you make it high?
Yes. Now is it properly audible?
Yes, sir. Yes, sir.
Yes.
Thank you.
Okay. Good morning, everyone. So myself Shardav Bhatt, and I'm going to give this webinar today on graph theory and its applications using Python. I would like to thank Salma madam for all the support for arrangement of this webinar. I would like to thank Dinesh Panchal sir for arranging this online platform for this webinar. I'm also thankful to Gaurav sir who has hosted this webinars today. And finally, I'm also thankful to Animesh sir who has created that nice poster which I have shared with all of you on the social media platform. And of course, thank you all of the participants who has arrived here to attend this webinar. So this webinar is basically on graph theory and its applications using Python. Graph theory is a subject which it's a part of mathematics, which I should say, which was derived from one of the real world problem, and today it is used in variety of fields. And we will see how useful graph theory is, and as a result, we will always have desire to make graphs of our own. We can make those graphs using Python. There are many other softwares available, but Python is open source. And as I will show you today, it will be very easy to create graphs in Python. So this webinar is a bit of introduction of graph theory and some of the Python codes related to it. So let us start. So you can see one of the region in this image. This image is taken from Google Earth in the recent year 2020, and you can see there is some river which creates 4 regions of some city. You can say this part of the city is different from this, and from this, and this is a 4th part. This area is situated in Russia, and the current name is Kaliningrad, and the river is Pregola river. Now we can see we need many bridges to connect different parts of this city. So in early days, in 1725, this was a map of Königsberg, and there were 7 bridges on this river. So you can see there are various bridges from one region to another region. We can go from this. Okay, we can go using these bridges. Now today, some of the bridges are not there. You can see in this figure, but in those days there were 7 bridges. So around 1725, the town people used to think of a problem, which is now known as a Königsberg 7 bridge problem. So people used to think that is it possible to start from one point, travel through all the bridges exactly once, and come back to the original point? Okay, it seems a simple problem, right? It seems a simple problem, but there are some rules, right? Like you cannot use any bridge twice. You cannot end up in with another region. You have to come back to the original place. Okay, and people in those days, there were no computers and nothing like I mean, maps were also not clearly available. So people used to actually walk on these roads and tried that is it possible or not, and somehow it it was not possible. Okay, so you start from here suppose you start from here, and then if you go through this bridge, okay, and suppose you go here, and now you're stuck here because you have used all the three bridges connecting this region. So somehow it's not possible. So the thing is, why it is not possible? The answer of which was given by a mathematician named Leonhard Euler. He was a Swiss mathematician. So he published a paper in around 1736, and that paper started this new subject of graph theory. Okay, so generally we mean by a graph that Cartesian coordinate system and all those things, but this graph theory is different from those things. We don't have any coordinates, we don't have any functions, graphs here. It is just about, we will see just two things are there in the graph. It's a very simple structure, but a deep level of mathematics is involved in it and variety of applications. So actually, this is a place where graph theory was born. I can say it was born using this using the solution of this Königsberg 7-piece problem. Now, is it possible or not, that we are going to see in today's webinar? There are several other problems that motivated this field of graph theory. One of them was a traveling salesman problem that was around 1800. So the problem is, suppose there is some salesman who has to travel different cities, and there are some distance given between different cities. So in which order he should select the cities, the path of the cities, in such a way that the minimum distance is covered. This type of problem was formulated by mathematician Hamilton and Kirkman, and this was also one of the early problems, real world problems, which was solved using graph theory. And this is a very well known problem, the 4-color problem, which was actually a conjecture in 1850s, but it was proven in 1976. So basically we can say it's a theorem, but it was conjecture before 1976. So that is a really interesting problem, that suppose you have a black and white map of some region. Is it possible to color the map using only 4 colors in such a way that the neighboring regions have different colors? Okay, this is one such example of it. You can see Madhya Pradesh is of blue color, and all the other neighbors of Madhya Pradesh are having different color than blue. You can see this. So at this small level, it seems it is possible. But what happens if we consider whole region? Suppose Gujarat has 33 districts. So is it possible to color all the districts of Gujarat using only 4 colors? Well, that we will see today by Python. So what is a graph? So graph is a very simple structure. It is denoted by G equal to VE, where V is set of vertices and E is set of edges. In Python, vertices are known as nodes. So we will refer vertices as nodes because all the Python functions are in terms of nodes. Okay, so basically vertices are nothing but dots or circles, whatever you can say. And edges are nothing but the connection between them. So you can see this is one simple graph. Okay, graph consists of basically only two things, vertices and edges. So there are various types of graph. First is simple graph. So each edge connects two different vertices and no two edges connect the same pair of vertices. This is an example of a simple graph. So basically you can see that there is one edge between every pair of vertices. That is a first condition, and there is no edge which starts and ends on the same vertex. So that is called a simple graph. Okay, so suppose if there are two edges between Denver and Chicago, then what will happen? Then it will not be called a simple graph. Or if there is an edge which starts from San Francisco and it ends at San Francisco, then this is also not a simple graph. So if you have such type of connections in your graph, then there is something called multigraph. So multigraph means there are multiple edges between the same pair of vertices. You can see there are three edges between Denver and Chicago. There are multiple edges between Chicago and New York, and so on. And suppose, as I told you, that there is some edge which starts at Denver and ends at Denver. If you have that kind of phenomenon, then that is called a loop. So loop means it's an edge that connects a vertex to itself. That is a loop. And if you have loop in your graph along with the multiple edges, then that graph is known as a pseudo graph. It includes loops and multiple edges. Okay. So we have simple graph, we have multigraph, we have pseudo graphs. This is the example of a pseudo graph. It consists of multiple edges as well as loops. Now, sometimes in our graph, directions are also very important. Directions in the sense that we have seen in a simple graph, we have something like this. Okay, and suppose this is Vadodara and this is Ahmedabad. So sometimes directions are important because if you are traveling from Vadodara to Ahmedabad, then you should have this type of edge. And that shows the direction associated with an edge. So if you have that type of edges in your graph, that is called a directed graph. Okay, so it consists of set of vertices and set of directed edges. Directed edges means the edges with some direction. So each directed edges is associated with ordered pair of vertices, u and v, where u is a initial vertex and v is a terminal vertex. In the example that I have shown here, v is the initial vertex because we are traveling from Vadodara, and a is a terminal vertex. Okay, because we are ending our journey at Ahmedabad. So that is what we have as a directed graph. Now in directed graph also, it is possible to have multiple edges as well as loops. So therefore we have multiple directed graph. So simple directed graph is nothing but simple edges with direction. Directed multigraph means there are more than one edge between two set of vertices, and mixed graph means a graph which is both directed and undirected is called a mixed graph. So we have seen 6 different types of graphs, and let us summarize this using this table. And from this table, we can see that there are 3 undirected graphs: simple graph, multigraph, and pseudo graph. These are undirected, and these are directed graphs. Okay. The last mixed graph means some edges are directed and some edges are not directed. Out of this, in which graph the multiple edges are allowed, that is written in this table, and in which graph loops are allowed, that is written in this column. Okay. Now, before going ahead, let us see the Python functions of all this type of graph. So in Python, we have 4 types of functions. nx.graph that gives us undirected graph with loops allowed, and parallel edges are not allowed. And then we have digraph. So digraph is nothing but a directed graph. And then we have a multigraph. So it's a multiple version of this graph, multiple edges. And if you have directed edges with multiple edges, then you have multi-digraph. Okay, so these are the 4 functions available in Python. Now let us go to the Jupyter notebook, which I'm using to explain you all the Python related stuffs. Okay. So actually we can use Python in variety of ways. There is something called Google Colab, in which you, without installing Python, you can work on it using your Google account in your Google Chrome browser. This is another nice way. And there are some nice IDs like PyCharm and Spider and Idle. You can use whatever it is, but I think Jupyter Notebook is very nice thing. So you can see in the Jupyter Notebook, we can write ordinary text along with code. So that makes it more better. Let me make it a bit bigger so that it will be visible to you. So the first, so we can create a graph in just 5 lines. The first step is importing a network X module. So those who knows Python will be familiar with the fact that Python programming language is based on different modules. If you want to perform certain tasks, you need to import that module. In particularly here, if I want to create a graph, for that there is something called network X. So network X is a module which allows functionalities to make a graph. Okay, and I'm importing as NX. So every time I don't want to write network X, so I can use NX as a shortcut of it. So in throughout the notebook, whenever you find NX dot something, that means network X is a module and graph is a function or a class belonging to that module. Okay, I mean, yes, graph is a class belonging to that module, and that graph has certain functions involving it. So to define a graph, we write G equal to NX dot graph. So that means we are saying that G is a graph. Now, since G is a graph, now we have to provide some nodes and vertices. Okay, nodes or vertices. So suppose I define this 4 vertices, A, B, C, and D. And then I can define edges like this. Okay, let me just clear all the outputs so that I can run in front of you. Yes, so outputs are cleared. So now, one by one, I'm running all the commands. So at this moment, there are no outputs. So this step number 3 is defining all the vertices. So I'm defining 4 vertices, A, B, C, D. And then I can define edges in following way. There is an edge between A and B, so I can write it in brackets like A and B. There is an edge between A and C, so I can write in bracket like this. There's an edge between A and D, so I can write it in bracket like this. So there are 4 edges in my graph. And now my job is to draw this graph. So if you want to draw this graph, the simple function is nx.draw bracket g. So if I run this, I'll have this simple graph on my screen. You can see 4 vertices and 4 edges visible to you. But still, this graph doesn't have many information. For example, which node is this? Okay, which is connected with all the vertices. From this, we can say it is A, but it would be great if it is visible here. So that I can write nx.draw bracket g with some additional arguments. And that additional argument is with underscore label equal to true. So this says that I want to draw graph G with labels. True means yes, I want labels. So let us run this. And now we can see the 4 nice labels, A, B, C, and D. Okay. So you have to pass additional arguments inside the bracket to do various things. Now here, I don't like this blue color because black font in blue color doesn't look good. I want to change the color of the nodes. What I can do? Well, for that also, Python has a nice facility. Along with G with labels equal to true, you have to write the third argument, node color equal to yellow. Well, you can use any color. You just have to write the name of the color inside that single quotes. Even double quotes are allowed. But the nice thing is that you don't need to remember color codes like other language like HTML and all those things. You can write the names of colors like yellow, light blue, sky blue, something like that. This is a very nice feature of Python. So let us run this. And now you can see nice yellow color. And now our nodes are nicely visible to us. Suppose I want to make edge color different. Well, then you have to give the fourth argument, edge color equal to red. And now you see my edges are red colored. Now, one thing you can observe that every time when I run this command, it gives a different direction, different configuration of a graph. Okay, that is also one unique feature of Python, because in graph theory, you will be aware of the fact that it does not matter in which direction you are preparing the graph. I mean, graph is a graph. Yes, sometimes it does matter that it should not cross some of the edges. Otherwise, it's in case of planar graph, it should not cross the edges. But otherwise, if you, in place of this graph, if you draw this graph, they are not different. Okay, they are not like mathematical functions that the shape change, then the the graph, the function change. It is not like that. You can draw in any direction. You can also make the size of this node color node larger by applying this additional argument, node size is equal to 100. So if I write this, and if I run this, then I'll have this type of things. You can see the nodes are larger than before. And even you can increase the font size within that nodes. So you can have font size is equal to 30. And now you can see larger fonts, larger nodes, different colored nodes, different color edges. You can customize your graph the way you want. There are n number of arguments inside this function nx.draw. These are some arguments that I have shown. You can explore more. Suppose you want to see, generally in textbook, we have seen the graphs like vertices v1, v2, v3, and so on. Suppose you want that type of graph, v1, v2, v3, and so on. So you have to write like this. And moreover, you can observe that here, when I define nodes and edges, I had to write 4 times. So if I have 10 nodes, is it possible to write 10 lines one by one? Yes, it is possible, but it takes so much time. So there is one more function in Python, add edge from. So if you write add edge from, you can see g.add nodes from and add edges from. So you can write all the things as a list. Okay, you can see I have vertices of v1, v2, v3, v4. This dollar sign represents that I want it v underscore 1. V underscore 1 means 1 is suffix to v. So it will be v underscore 1. Okay, and it's a mathematical thing, so therefore you have to put dollar. So if you put dollar, then this underscore will not be there. Okay, so it is inspired from LaTeX kind of mathematic structure. In LaTeX, we write the equations within the dollar. So exactly same way this works. Okay, and you can write edges like this bracket. So there is edge between v1, v2, there is edge between v1, v3, and so on. So let us try to run this and let us see how we get. So you can see v1, v2, v3 all are in suffix, right? So now our graph looks exactly as a textbook graph. We can also draw a directed graph. So for directed graph, you have to define a function multi-digraph. And here you can see the directed graph. Okay, and you also have to pass this additional argument, connection style equal to arc3, radius equal to 0.1. So if you run this, you will have something like this. So this radius 0.1 is nothing but the radius around this loop. Okay, so this is a multi-digraph. We can list out vertices and edges of a graph. So suppose this is my graph and I have some 6 edges. So I want to see how many vertices, 6 vertices are there. So I want to list out all the vertices and number of vertices. So g dot number of nodes gives us the number of vertices, and g dot nodes gives us all the list of nodes. So let us try to run this, and you can see the number of vertices are 6, and these vertices are A, B, C, D, E, F. Similarly, you can have number of edges and list of those edges. You can see there are 9 edges and they are A to B, A to C, A to D, A to F. You can see A is connected with 4 vertices, E is connected with only one, that is D, and there it is, D is connected with E. Okay, now let us come back to the presentation. So these are some applications of graph. So this is an acquaintanceship graph. Such type of graphs are used in social networks. Okay, so for example, Kamini is a friend of Jan, but she's not friend of Paula. So so Kamini, so you can say that Paula. So if Kamini is not friend of Paula, then Facebook will give suggestions to Kamini that you may know Paula. Okay, we get such type of suggestions on Facebook and Instagram. So behind that, the social network plays a major role. In fact, there is one nice concepts in computer science. There is something called social network, 6 degrees of separation. 6 degrees of separation says that between any two person of the world, there are only 6 other peoples connected. Okay, well, this is a conjecture. It is not proven yet, but it is true for a really big network. So as per this conjecture, you have a connection with, you can say, Donald Trump. Well, I can say Biden now because Donald Trump is not a president now. So you and Biden have connection between 6 people. Now, how that connection is there? Well, that's a different story. But in large Facebook and Instagram social networks, this thing has been proven. Okay, and so that is proven using this. So, for example, here Kamini and Kamlesh are connected by 1, 2, 3 people. So there's a 3 degrees of separation. Okay, so just assume here you are there and here Donald Trump is there, or your favorite celebrity. There is a connection of 6 or less people. Okay, so that concept is based on graph theory. Graph theory has also application in influence graph. So here, which person is influencing the other person? That is represented by this directed graph. You can see directions are involved. Another application is a call graph. So call graph is also a directed graph because from which number to which number the call is going, is it incoming or outgoing? That makes a difference. Another application in computer science, that is a module dependency graph. Different modules of programming language, which module is depending on which previous module or function or class, whatever it is. So that can be used by the software engineers. We can also have something called a precedence graph. So in that shows that the statement, which statement is preceding the other statement. For example, you can see S3, for S3 you need value of A, so S3 depends on A, but S3 does not depend on S2 because B is not required for for this statement 3. So S3 is not connected with S2. So such type of graphs are also there for the programming languages. This is a niche overlap graph, which represents the type of food shared by different people, different animals. Sorry, you can see a crow and owl shares. There is an edge between owl and crow because they share a same type of food, but crow and woodpecker don't share a same type of food, so there is no edge between them. So this type of graphs are used in biology. And in microbiology, this type of graph is used. This is a protein interaction graph. Our body is full of different type of protein. Which protein is interacting with which other type of protein, that is given by this protein interaction graph. And this is a graph which is used in linguistics, the semantic network of nouns with similar meaning centered of the word mouse. So when we use word mouse, we either refer to it as a computer mouse. So in that case, desktop, keyboard, trackpad, all the things are associated with this, or we refer to mouse as a animal, so which looks like a rat or similar to the rabbit family, right? So on one side you have all the animals, on the other side you have all the hardware of computers. So this is related to grammar. I mean, mouse is a noun, and these are the related words to this thing. So in the linguistics also graphs can be used. And of course, our favorite, graphs are used for round robin tournaments. Currently, the IPL is going on. In IPL, every team plays with every other team. So if we put an edge between them, that means that match between those two teams has been done. Okay, so in IPL there are two matches between every pair of teams. So there are two edges. This is graph of 2019 Cricket World Cup, which was also a round robin tournament. Now there are some terminologies of graphs like neighbors. Neighbors means if a particular vertex is joined with other vertex, those all the other vertices are known as neighbors of a particular vertex. And there is something called a degree of vertex. So degree of vertex is nothing but number of edges connected with a particular vertex. And for that, the Python functions are g.neighbors and g.degree. So let me take you to this Python. So we'll refer to this same graph that we have already seen. So neighbors of vertex C are A, B, and D. You can see C is connected with A, D, and B. So they are the neighbors of it. We can find all the neighbors of all the vertices using this for loop. So in using this for loop, you can see neighbors of A are B, C, D, F, neighbors of B are A, C, D, neighbors of E is D. Okay, you can see from this graph, it is satisfying all the conditions. We can find the degree of all the vertices using the function called g.degree. So you can see A, he's having degree 4, B is having degree 3, C is having degree 3, D is having degree 5. You can see D is at center having degree 5. And you can also print a particular the degree of a particular vertex. So degree of A is 4. And these are a degree of all the different vertices. So degree of A is 4, B is 3, and so on. You can write like this. Now we will see some different types of graphs. So some special simple graphs. So first is a complete graph, which is denoted by Kn. So complete graph is nothing but there is an edge between every pair of vertices. And for that, the function is nx.complete graph. You can see some complete graphs on your screen. There are cycles which are denoted by Cn. So cycles means they are connected sequentially. Okay, so A is connected with B, B is connected with C, C is connected with D, and D connected back to A. So that creates one kind of cycle. So cycle for different type of vertices are shown here in the figure, and these are the this Python function for it that we will see soon. And there is something called wheel. In wheel, there is one vertex at center and all the other vertices are around it. And these are some examples of wheels. And we can see nx.wheel graph is a function for this. And then there is something called complete bipartite graph. So in complete bipartite graph, the vertex set is divided into two parts, K23 and K2. So K23 means two vertices on one side, three vertices on the other side. And there is an edge between one vertex set to another vertex set. There is no edge between the vertices of the same group. There is no edge like this. Okay. So that is what we have. And for that, the Python function is nx.complete bipartite graph bracket mn. Okay. So the function for them are also very simple. You just have to write nx.complete underscore graph and bracket 5. So that will give us complete graph of 5 vertices. There it is, complete graph of 5 vertices. For cycles, we have to use nx.cycle underscore graph. That will give us a cyclic graph of 5 vertices. So you can see a cycle of n equal to 5. If you change this, you will get a different thing. You can see if you add 7, then you will have a cycle of 7. You can change this number. And then you have wheel. Okay, wheel of 6 vertices. You can see here the wheel of 6 vertices. So for that, nx.wheel underscore graph is the function. You just have to remember all this function. And then last is complete bipartite graph. So for complete bipartite graph, the name of function is same, complete underscore bipartite underscore graph. And for that, you have this thing. You can see the complete bipartite graph, 3 vertex on other side, 2 vertex on other side. Okay, but by plotting this graph, during plotting this graph, you have to take care, you have to write this layout, nx dot drawing dot layout bipartite. So you have to divide the set into the two set of vertices, 0, 1, 2 on other side, one side, and 3, 4, 5 on other side. If you don't write this, let us see what happens. If you don't write this, then it will look something like this. You see, it is still a bipartite graph, but you will not feel that it's a bipartite graph. So the layout should be mentioned. That's drawing.layout, bipartite layout. That will give us this thing. Now there's something called adjacency matrix and incidence matrix in graph theory, which is given by this definition. So if there is an edge between two vertex, then you have 1 in a matrix, otherwise the entry is 0. And for that, the Python function is adjacency matrix. Similarly, incidence matrix means particular edge is incident on particular vertex or not. If yes, then 1. If no, then 0. The Python function is this. Okay, so let us see. Suppose this is our graph. This is the same graph that I have shown you above. So what is an adjacency matrix of this graph? So it will be a 6 by 6 matrix because there are 6 vertices in this. So for that, you have to use the function adjacency underscore matrix, and then you have to use this additional function toDense. If you don't use this function toDense, then what will happen? It will show only the entries with 1, and the matrix layout is not visible. So if you want a matrix layout and also the entries with 0, you have to write toDense. And similarly, you can have an incident matrix. Incident matrix is going to be a 6 by 9 matrix because there are 6 vertices and 9 edges in our graph. So this one entry shows that there is an edge incident on first vertex and the second edge. Okay, next is paths and circuits. Okay, so what is a path? So suppose you have a graph. Suppose you have a graph like this. Okay, and suppose you want to travel from this vertex A to this vertex B, then you will go this way. Suppose I also have this type of thing. Okay, you will go in this direction like this. So this is one such path from A to B. And if you go this way, then this will be another path. Or the third path is also possible, in which you can take a turn from this and you can take all the long route. Okay, so this is called a path. Okay, so this is just a mathematical definition of it. And you see, if you consider Kamini and Kamlesh, then there is a path of 6 people linking Kamini and Ching, not Kamlesh, Kamini and Ching. You can see. So if we consider a path from Kamini to Jain, Jain to Paula, Paula to Toad, Toad to Kamlesh, and Kamlesh to Ching. So including Kamini and Ching, you have 6 people. Okay, but this path is not unique. You can also go following path. Okay, but a path is called simple if you don't use a particular edge more than once. So that is called a simple path. Okay, the Python function for simple path is nx.all simple path, and then you have to give 2 arguments, g, a, and b, where g is the graph, a and b are so a is a starting vertex and b is a terminal vertex. Okay, so let us see how this works in Python. So actually there is something called connected graphs, but that section is later, so I'll show you later. So suppose this is my graph. Okay, so if I write like this, for loop for path in nx.all simple graph gab, that it lists out all the paths between A and B. So how many paths are possible? You can see there are so many paths. Okay, so this is A and this is B. So one path is directly from A to B. Another path is ACD, ACB. So ACB, this is another possibility. The third possibility is ACDB. Okay, ACDB. Okay, and remember all these paths are simple paths, so edge will not repeat. Okay, but if you want a shortest path out of this, suppose I want a shortest path between A and E, then you can write nx dot shortest path. So that will give us ADE. ADE. Okay, so this function is very useful if you have a very large graph. In large graph, if you want to find uh, the path between different pair of vertices. And what is the length of the shortest path if you want? That you can find using shortest underscore path underscore length. Okay, so this is what we have. Let us come back to the slides. And then there is something called a circuit. So circuit is nothing but one type of path. But when you start from a particular vertex and come back to that vertex, then that is called a circuit. Okay, so you can see if u is equal to v, okay, the circuit is, as it's a path, it begins and ends at the same vertex. So circuit is just one type of path only. It begins and ends at a same vertex. Okay, and path and circuits are called simple if it does not contain same edge more than once. Okay, if edges are used only once, then they are called simple. So that function already we have seen. So this is just an example. So you can see A, D, C, F, E is a simple path. D, C is not path, and so on. Okay. And now we will see connected graph. So connected graph means if there is a path between every pair of vertices, then that is called a connected graph. And if it is not there, then it is called disconnected graph. Okay. So connected and disconnected graph, the function to do this is function to check this is nx dot is connected g. Okay, so that will give us answer true or false. Okay, so this is an example of connected and disconnected graph. G1 is connected because there is a path between every pair of vertices. G2 is not connected because from E to A you cannot go because there is no edge between them. So this is a disconnected graph. Okay, so let us come back to this and check the connected graph function. So suppose this is my graph. Okay, and you can see in this graph there are three vertices together and this fourth vertex is away from them. So basically this is a disconnected graph. We already know this. You can use this function nx dot is connected bracket g. The answer is false. That means it is not connected. Okay, it's just like a question, is it connected? False means no. This is a second graph. So here we can see there is a path between every pair of vertices, and so if you run this, nx dot is connected, that will give you true. Yes, there is a path between every pair of vertices. It's a connected graph. Now next is Euler circuit and Euler path. So what do you mean by Euler circuit and Euler path? So it is a special type of paths and circuit in which you cover all the edges of the graph. Okay, an Euler circuit in a graph of G is a simple circuit containing every edge of G. Okay, that means uh, it's not about a shortest path. It's about covering all the vertices, all the edges of the graph. That is called an Euler circuit. So it is one type of circuit only, and same thing for path also. Okay, so if you start from a particular vertex, if you travel all the edges exactly once and come back to that vertex, then that is called and Euler circuit. And if you start from a particular point, cover all the edges of the graph and reach at some particular point, that is called Euler path. And so these are some examples of Euler path and Euler circuit. but we will see a practical example. Now, how will you know that whether our graph has an Euler circuit or Euler path or not? For Euler circuit, there is one theorem which says that if every vertices of graph has even degree, then that graph should have an Euler circuit. Okay, so a graph has an Euler circuit if and only if its vertices has even degree. That this great theorem was given by Euler and which helped to solve the Königsberg 7-bridge problem. Well, how it was helpful, let us see. So you can see this was a problem. Okay, so first of all, we need to convert this problem into graph theory. So we assume that all the regions are vertices and all the bridges are edges. Then what will happen? So suppose you have this type of 4 regions. So we can see there are 2 bridges between these 2 regions. There are 2 bridges between these 2 regions also. So I have something like this. There is one bridge between this central region. So there it is. There is one bridge from upper to right region. So this will be my graph. Okay, this will be my graph. So if you convert this problem into graph theory, then your graph will look something like this. Okay, your graph will look something like this. Now, what was the question? Remember, is it possible to start at some region covering all the bridges exactly once and reach back to the original region? That was a question. This question is as good as asking, can we find an Euler circuit inside this graph? Because Euler circuit says that you have to start from one point, you have to come back to that point in such a way that you have to cover all the edges here. Okay, now edges are bridges here in our problem. Edges are nothing but bridges. We have to cover all the bridges. That means we have to cover all the edges. And that means you want to find an Euler circuit inside that graph. Now remember that theorem which says that the theorem that says that the degree of all the vertices should be even in your graph. If that is there, then you can find the Euler circuit. In our graph, you can see the degree is not even. Some vertices are having 3, 5, 3. I mean, all the vertices are having odd degree. And therefore, you cannot find Euler circuit inside this graph. And since you cannot find Euler circuit inside this graph, you cannot travel in such a way that you start from one point and you can reach back to another point by covering all the bridges exactly once. This solution was given by Euler in 1736 as a research paper, and that was, I must say that was a point where the graph theory was born. Okay, so we have this Euler circuit and solution of Königsberg 7-bridge problem. So I'm creating that same graph here. So I have 4 vertices A, B, C, D, and there is an edge between A, B, 2 edges between A and B, 2 edges between A and C, 1 edge between A and D, and so on. Okay, and I'll print the degree of all the vertices, and then I will use a function is Eulerian. Okay, is Eulerian says that whether it has Euler circuit or not. Let us run this, and you can see the degree of A is 5, B3, C3, D3, and the answer is false. That means our graph does not have an Euler circuit, and since it does not have an Euler circuit, you cannot have a solution of Königsberg 7-bridge problem. Okay, now the next application, we will see 2 more applications. They are very interesting. The next application is, this is just a solution of this thing. Okay, so this, you can see something on your screen which is known as Traveler's dodecahedron, which was a puzzle in 1850s. Okay, so the puzzle is something like that. You can see there's an umbrella shaped thing which is known as a dodecahedron. Okay, so on dodecahedron there are some dots given. So each dot represent a city, and there is a path between that city. Okay, and then this thread is given to you, so you have to use the thread on different vertices of this dodecahedron. Okay, so the puzzle is that you have to start from particular city, you have to cover all the cities on this dodecahedron and come back to the original city. Okay, so there were 20. So this was known as Icosian puzzle, which was given by Hamilton. So this was a wooden dodecahedron. There are 20 vertices of a dodecahedron. Okay, and they were labeled the names of different cities of the world. So puzzle was to start at a city and travel along all the edges of the dodecahedron and come back to the first city. Well, this puzzle was very difficult in those days, but if you convert this into graph theory, it's very simple. So the graph theory version of that was given by Hamilton path and Hamilton circuit. So Hamilton path and Hamilton circuit, they are nothing but simple graph in which they are simple graphs in which a path passes through every vertex exactly once. Okay, remember in Euler's path and Euler circuit, we cover all the edges exactly once. In Hamilton path and Hamilton circuit, we cover every vertices exactly once. And so we have this graph version of that puzzle dodecahedron. So this shape is known as a dodecahedron. If you draw it in 2 dimension, it will look something like this. So can we create a path which starts from a particular vertex, covering all the vertex exactly once and come back to the original vertex? Well, it is as good as asking, can we find a Hamilton path inside our Hamilton circuit inside our graph? Well, it turns out, yes, it is possible. You can see this blue colored line is nothing but a Hamilton circuit inside our graph. And as a result, what will happen? The puzzle is solvable. Okay, this solves our puzzle. It looks very simple on our screen, but when you actually solve that puzzle, you can see the shape of that dodecahedron. It's very complicated. Okay, so if you want to make a traverse dodecahedron in Python, there is a function called nx.dodecahedron graph. And you can see this is a 3-dimensional version of that graph. Okay, if you want to see from different angle, you have to run it again and again. You can see from different directions. Okay, so once you have a circular kind of thing, it's very difficult to do this. And these are some information about this dodecahedron. Number of vertices are 20 because 20 cities are there. Okay, number of edges are 30, and these are list of vertices, list of edges, and the degree of all the vertices. So all the functions that we have used earlier we are using here again. Okay, and now we are going towards a very nice problem which is known as 4-color problem. But before that, we need to study what's a planar graph. So the planar graph was motivated by this example, that suppose there are 3 houses and 3 utilities like gas, water, and electricity. If I want to provide these 3 utilities to these 3 houses in such a way that there is no crossover of the services connections, okay, then if it is possible, then it's called a planar graph, otherwise it is not. Okay, so you can see there are already so many crossover of edges. I don't want crossover of edges in my graph. If that is possible, then it's known as a planar graph. Okay, so what is a planar graph? It's a planar graph is a graph which can be drawn without any edges crossing. So in figure one, you can see the 2 edges are crossing, but I can solve this by putting this edge like this. So you have something like this, and as a result, now this is a planar graph. Now look at this graph. Do you think it's a planar graph? Is it planar or not? Well, there's a 3-dimensional cube. Okay, so if you draw this cube in different way, then it is possible that it is possible to represent it in planar representation. So you can see this is a planar representation of this graph. Okay, and hence this is also planar because no edges are crossing. Earlier there were 2 edges which were crossing with other 2 edges. The Python function to check whether our graph is planar or not is nx.checkplanarity. Okay, so let us see this in Python. So I'm creating a complete graph of 4 vertices. So that is this. And you can see there is edge crossing here. But is it possible to draw this graph in such a way that the edges are not crossing? So for that, I need to check the planarity of that graph. So let us run this. It says true. That means yes, it is a planar graph. Okay. So the function is nx.check planarity. And you can draw this in planar form by giving this function nx.planar layout. Earlier we have seen bipartite layout. So there is something called a planar layout. So if you run this is a planar layout of the same graph. You can see now the edges are not crossing. So Kartowski is the name of one of the mathematician who helped us to give a theorem which says that whether a graph is planar or not. So he gave two graphs. The first graph, which is a complete graph of 5 vertices, which is denoted by k phi, which is not planar. He gave another graph, which is k33, which is nothing but a bipartite graph with m and n equal to 3. Is it planar? Well, it is also not planar. Okay, you can check later whether it is planar or not by drawing this in different way, but actually they are not planar. Kartowski told that, so before that, what Kartowski told, let us check this solution of utility problem. So you can see if you represent the three houses with 3 vertices and 3 utilities with other 3 vertices, there is a connection between them. So basically this graph is nothing but K33, and as a result it is a Kartowski's second graph and it's not planar. Okay, and so this is how graph theory is used to solve the utility problems also. But what Kartowski told us is, so this is subgraph. Subgraph is nothing but removing some edges and vertices will give us a new graph. So from G you have H, that is called a subgraph. So what Kartowski told that if you have a graph and if K33 or K phi is hidden inside your graph, that means if K33 and K phi is a subset, is a subgraph of your original graph, then your graph cannot be a planar graph. And that theorem helps us to check the planarity of a graph. Okay, so suppose you have a graph of 1000 vertices. You don't need to check all the things. You just have to check whether K33 is hidden inside this, K phi is hidden inside this or not. Okay, so from that you can do it. And of course, Python also help us to check the planarity using the check planarity function. Okay, so let us check. This is Kartowski's first graph, which is not planar, so false. And this is Kartowski's second graph, which is K33, and that is also not planar. And any graph which is a superset of these two graphs, they cannot be planar. Applications of planar graphs are electronic circuits and root networks. Okay, so even an electronic engineer can use graph theory for this purpose. And now the last application of our webinar, and this is a very nice application. Suppose we have this black and white graph in which colors are not there, and suppose you want to fill it with colors. How many minimum number of colors will be required? Okay, you can see, suppose Rajkot is connected with so many things. 1, 2, 3, 4, 5, 6 or 7 districts are connected with Rajkot. Is it possible to color this graph using only 3 colors or 4 colors or 5 colors? So for that, you need to convert this map into the graph. This is map. Okay, we need a graph version of this map, and that is done by dual of a map. So dual of a map says that every cities will be represented by a vertex, and if two cities are neighbors, then there is edge between those two things. Okay, every cities will be represented by a vertex, and if they are neighbors, then there is an edge between them. Okay, so the resulting graph is a dual of a map. So you can see, suppose this is your map, then what is the dual of this map? So it is nothing but a graph version of this. You can see A is connected with B, C, D, and E. So in graph also, A is connected with B, C, D, and E. All the things are satisfied here. So the thing is that can we represent our Gujarat in terms of a graph? The answer is yes, definitely. Why not? There are 33 districts. So there are 32 vertices in our graph, right? And so suppose Rajkot is having 7 neighbors like Porbandar, Jamnagar, and so on. So there will be an edge between Rajkot and all those cities, and there will be no edge between Rajkot and Vadodara. Are you getting this? So yes, it is definitely possible, and let us try this in Python. So that we will see. So we will get a graph something like that. We will see this later. But first, I would like to introduce you with the graph coloring. So graph coloring is nothing but coloring the vertices of a graph in such a way that the no two neighboring vertices have the same color. Okay, so this there's something called a chromatic number of a graph. So chromatic number is nothing but the number of colors required to color a graph, minimum number of colors required to color a graph in such a way that the neighboring vertices does not have the same color. Chromatic numbers is denoted by chi of g. And these are some famous graphs that we have seen: complete graph, cycles, wheels, and complete bipartite graph. So chromatic number of all these graphs are n, 2 and 3 in case of cycles, 4 and 3 in case of wheels, and 2 in case of bipartite graph. So bipartite graphs can be drawn with only 2 colors. Wheels can be drawn only with 3 or 4 colors based on the number of vertex. If it is even, then 4. If it is odd, then 3. Let us see this in Python. So I'm creating a complete graph of 5 vertices here, and I'm using this function. Okay, so the function, Python function for this is nx dot greedy color of g dot values. So that will be helpful for us to decide the chromatic number of the graph. So you can see, if I use this function, then it gives me answer like 0, 1, 2, 3, 4. That means 5 different colors are required to color this graph. Okay, if you consider this wheel, then in case of wheel, you have 0, 1, 2, 0, 1, 2. Okay, that means only 3 colors are required: 0, 1, and 2. This 1 and 2 are repeating because we have 5 vertices. So suppose if you have 8 vertices, then you have 0, 1, 2, 0, 1, 2, and 3. So if you have even number of vertices, you will need uh, 3. You can see in case of odd, it is 3. So yes, so this is what you have. Okay, so greedy color basically helps us to find the chromatic number of a graph. Okay, similarly, cyclic graph. So you have 0, 1, 0, 1, and 2. So basically 3 different colors are required for our graph. And of course, complete bipartite graph, there are only 2 different colors are required. Okay, and now we will see the problem of our Gujarat state coloring. Okay, so there is something called a 4-color theorem. 4-color theorem says that if you have a planar graph, then 4 colors are enough to color the graph. Okay, so if the graph of Gujarat that we made, if it is planar, then we can definitely color the Gujarat map, the map of Gujarat, using only 4 colors. Well, that is going to be very interesting. So for that, I need a list of districts of Gujarat. So what I have done is, so I would like to show you in Excel. So there it is. So in sheet 1, I have all the list of 33 districts of Gujarat. Okay, I have written separately in Excel because I don't want to make my program look very messy. So I will write it in Excel, and then I'll read from Excel. And then in sheet 2, I'm writing the neighbors. So neighbors of Ahmedabad are Anand, Bhavnagar, Botad, and so on, and so on. You have Amreli has different neighbors, and so on. So this file is there, right? I need to I need to read this file from Python. So for Python, for that, your file should be in same directory as your Jupyter notebook. and you have to use pandas. So import pandas as PD. So I'm reading sheet 1 and sheet 2 using different 2 lines. And then I'm listing out all the districts of Gujarat using list of sheet 1 0. So in sheet 1, you have districts. So I'm making it as a list. And you can see here, all the names of districts are visible here. Similarly, we can make a list of neighbors of districts using neighbors dot append command. Okay, so you have this different type of neighbors, right? And finally, we can create a dual of a graph. So for that, what I'm doing, I'm adding the nodes from the districts, and I'm adding the edges from the neighbors. So what are districts? Districts are nothing but this. That means nodes. And what are neighbors? Neighbors are nothing but this, which represents edges. So I have defined a graph. I have defined districts, neighbors, nodes, vertices, and let us see. I have 33 districts, so 33 vertices, and 71 pairs are there of neighbors. And so what is a dual of that map? So I can draw this map now, and you can see I have a graph something like this. Okay, but I don't want a graph here. I want a graph in a separate window. So for that, you can use matplotlib qt5. Okay, so if you do this, you will have a graph in a separate window. So we can see this now, this nice graph. Okay, you can see Rajkot has different neighbors. Now this map, this graph will not similar to the map, because see, it will be similar, but it will not show the exact positions, but it will show the correct neighbors. You can see Vadodara has neighbors Bharuch, Narmada, Chota Udaipur, Panchmahal, Kheda, and so on. Okay, so this is how you can get a graph. And now let us check whether it is planar or not. So for that, we have seen a function check planarity. Yes, it's true. It's planar, and if it is planar, definitely we can draw that using only 4 colors. So our Gujarat can be colored in only 4 colors. So for that, I'm using again this function greedy color, and so these are the values of different colors. So these are 33 different values corresponding to the 33 districts. So you can see first 3 colors are 0, 1, 0. The first 3 districts are Ahmedabad, Amreli, and Anand. So Ahmedabad has color 0, Amreli has color 1, and Anand has also that 0 color, right? And once I have 0, 1, 2, and there is 3, so I need 4 colors. There is no 4, so fifth color is not required. So for each of this number, I can define a color. So I'm defining these colors like coral, green, yellow, sky blue, and plum. So if if the if the code is 0, then it's a coral color. If it is 1, then green, yellow. And using that, if I make a graph, it will look like this. You can see Gandhinagar having purple color. Okay, so actually it's not purple, it's plum color. Then all the neighbors of Gandhinagar does not have the plum color. Okay, so this greedy color algorithm helps us to color our graph in such a way that the neighbors do not have the same colors. And that's the solution of our problem. We wanted to color a map of Gujarat using different colors. Okay, so this is a map of, this is a dual of a map of Gujarat. And now I'm going to color them using these colors. So remember, you can remember some of the colors, like Vadodara has red color, and Surat has blue color, Narmada has green, and Bharuch has plum color. Okay, so now we are going to use exactly these colors. So this is our black and white map. Let us first use all the red colors. Okay, so these are all the red colors, and you can see at this moment, no two neighbors are having same color, because this is just one color. Now let us introduce a green color in our graph. Yes, still green is not connected with green, red is not connected with red. Now let us introduce a third color, that's blue. Still it is maintaining the rules of coloring. And finally plum color. And you can see our map is colored with this. Okay, now this coloring I have not done using Python, because Python gives me the information up to this, that you have to use this color for this district, and then later using some software I have colored this map. Okay, so that's it for the webinar. These are the important bibliographies that I've used for this. So some of the images are taken from this websites. I've mentioned them. And this book, I've taken the theoretical part from the Discrete Mathematics and its Application by Kenneth Rosen. And this second book is very important, NetworkX Reference Release 2.6, in which all the Python functions related to graphs are given. So thank you for attending this webinar. I hope you liked it. I hope you enjoyed it. If you have any queries related to graph or Python or anything, you can feel free to contact me. My PPT and code will be available on the ResearchGate website. I will upload it by today evening. And the YouTube link for this webinar is also available, which is I'm mentioning here. So if you want to revisit this webinar, you can visit the Navrachna University YouTube page and you can go through this. So that's it from my side. Now, if you have any questions, then we can discuss, or we can stop here.
Thank you, sir. It was so informative. Very
Yes.
informative.
Welcome very much.
Participants can unmute themselves and ask questions. Murtuja, you can ask question directly to sir.
Yes, if you have any question, you can ask me.
Sir, there is
Sir,
one
can
question
you please
from...
suggest me any book for this software Python?
Yes, definitely. There are many books available in market. So I think you can mail me. The email address is available to you. You can mail me. I'll suggest 2 or 3 books, and I'll share it with you.
Thank you so much, sir. Thank you.
Yeah, welcome. So is there any question? Let me go to the chat section.
Any question? There is no specific
Okay, I've
chat.
gone
I'll
through
check.
the chats. Yes, I don't think there are any questions, but all of you, I'll still tell you that if you have any, if you need any guidance related to Graph or Python, you feel free to contact me using this email address. And again, thank you very much. Okay, there is one question from Kandarb. What are the other areas of use of these things? Well, Python has variety of areas, and some of which I have not included in my sites. So, for example, it is used in chemistry for the interaction between two different components. It is used in computer engineering. It's used in even the astronomy also. The different different. I mean, if you specify in which area you are, then I can give you the application of your area. I can find the application and I can mail you. So Kenneth Rosen says that almost every conceivable discipline have the applications of graph theory. Okay, not only science, but also in commerce and financial and all the other things. So if you can specify a particular field, I can definitely find some applications related to you. And can we make this thing in 3 dimensions? Well, yes. The 3 dimension, we have already seen one of the graph, the 3-dimensional graph, that cube graph is also there. And we saw the planar representation of that graph. That's very much possible. three dimension, means we can represent three dimension in our paper or in our computer screen. But in reality, if you want a 3D graph, then you might need a 3D printer maybe. There is one more question. Can we use it in differential equation Python? Okay, so your question is, can we use Python for solving differential equations? Yes, Python can be solved for Python can be used to solve any mathematical problem. Just remember, Python can be solved not only for mathematics, even for developing softwares. Python are very useful. There is one more question. Is there any good book for fundamental theorem for Nash equilibrium in graph theory? Well, I'll go through the books of graph theory and I'll come back to you. So this was a question. So this was question from Richa. So Richa, you can connect to me by Gmail or a ResearchGate. I will definitely find a good book for you related to this Nash equilibrium. I have a couple of books. I'll go through that thing if it is possible in this or not. Can graph theory be used in neural networks? Well, neural networks are itself one type of graphs. Okay, even hidden Markov models are neural networks. They are all graphs. See, in neural networks, we have some weights associated with the edges. Okay, so there is something called weighted graphs in graph theory. So definitely in neural network, we can use the graph theory. Definitely. That was a really nice question by Murtaza, connecting two different fields of graph theory and along with machine learning. And neural networks are also my field of area of research. So I'm very happy with this question. Sir, I'm an old user of Python, but new to graph solving is best book for beginners.
आप बहुत सोते सारामा सारा सर.
So Kandarp Solanki is asking this question. That's so your question is regarding which is best book for beginners, right? For related to graph theory, well, I will just take you to the previous slide and this second book, the Network X reference module, which is freely available in this link. This book is good if you want to learn Python graph theory. And I'm very happy to know that the old user of Python has also participated in this webinar, who learned something new. That was the main motive of this webinar, that connecting the theoretical aspects along with Python implementation. That's I'm very happy with your question. So anyone else has a question?
Okay.
I think
I believe we are done, Shardov sir. I request Salma madam to offer vote of thanks.
yes.
Yeah, thank you, sir.
Is there any other question? Yeah, Shardov sir.
Yes.
Please go on.
So if any further questions are there, then feel free to contact me on my email address. I'll definitely answer your queries. And thank you everyone to attend this webinar. And it was my first webinar. So and I was very excited for that. And you all participated in this, and you came and you motivated me. So I'm very thankful to all of you. I'm also thankful to Salma madam, Gaurav sir, Animesh sir, Dinesh sir, and the Navrashna University for giving me this platform. Thank you, everyone. Salma ma'am, you can.
Salma madam,
Yeah.
please.
Yeah, yes, sir. Thank you, sir. So first of all, I would like to congratulate Mr. Shardav Bhatt for very well explain this session on graph theory, because I can see graph theory is a like pure mathematical subject, and actually I also earlier felt that like it will be difficult to understand the concept, but I could see that the Sharda has explained, like started with a great like application, example, history, and for each concept he has started with some real application and then switched to the Python, and I could see like very nicely arranged session was there. So I'm very happy, and I hope that each participants will feel like this also. So very well. Thank you so much, Sharda, for
Thank
such
you,
an
madam.
informative and very well explained. And I could see that you have done great efforts. Like you have done very hard work for this, because like everything you have typed, all this command in Python and presentation as well.
Yes,
So
ma'am.
I'm really appreciates your efforts.
Yes,
And
exactly.
I am also yeah, I'm thankful to first of all our Navaratna University and mainly our provost sir, Professor Nilan Yajnik sir, that who has started this initiative and started this platform on which we can come and speak for our subject, and we can show the application of mathematics subject, like because everyone feel that non-mathematical people feel that the mathematics is very difficult subject and we cannot find some real application. But this I am thankful to our provost sir that who has given this opportunity to us, that every faculty come forward and speak about their subject. And yeah, I am also thankful to Dinesh sir for hosting this, and who has started this you can say task, and obviously Gaurav sir also, that today he has devoted so much time for us for hosting this session, and of course Animesh Bhatt sir, and all the mathematics faculty in our team, Navrashna University team, and last but not least, all the participants who had attended this lecture, and they have given very nice feedback also to sir, Shardav sir, and like nice interactive session they have made. So I am deeply thankful to one and all. Uh, audience also. So yeah, so this I can end my session here. So anyone wants to speak
Okay.
anything else? So otherwise we'll stop.
Sorry to interrupt you, ma'am. Can we have certificate for the attendance?
No. There is no
Okay.
certificate.
Okay.
In
No
in
problem. No
our
issues.
in
No
terms of
issues, sir.
certificate, I will give you my PPT and my code to you.
Okay, sir. Thank you.
Yeah,
So
Thank
that
you.
will be kind of
that will
certificate to
be
you.
that will be
Yeah,
Okay,
that
great
will
sir.
help
Thank you.
for
you will
everyone.
be able to
That is more than,
you will be able to use it in your work.
Yeah,
Okay, sir. That's great. That's great. Thank you, sir.
Yes.
that is more than certificate, I believe.
Yes, exactly.
yeah,
Yeah,
that's
yeah.
true, sir.
Exactly. Yeah.
Okay, so thank you everyone. Thank you participants. Sardar sir, Salma ma'am.
Yeah.
Now we
Thank you.
are
Yeah, yes,
going
sir.
offline now.
Yeah, sure.
Thank you everyone for participating in this wonderful seminar, excellently explained by Sardar sir. Thank you very much, sir.
Yeah.
Yeah.
Good day, sir.
Thank you.
Good day to
Thank you, sir.
everyone.
Thank you,
Good day
Gaurav
to
sir,
everyone.
Shadav sir, and all the participants.
Yeah.
Okay.
Okay, all of you. Okay, have a good day. Let's
Yeah.
Okay.